This is neocortex, a sheet of cells just a few millimeters thick, covering the surface of the brain. It is the most recent addition in our evolutionary history, and it's the structure responsible for nearly everything we consider uniquely human, from language to abstract reasoning. For decades, scientists have tried to reverse engineer this remarkable tissue, but a deep mystery has always remained. What are the unifying principles governing the coordinated dance of billions of cortical neurons? In recent years, a powerful new framework has emerged. The thousand brains theory, pioneered by Jeff Hawkins and the team at Numenta, proposes a single, elegant explanation for what the neocortex does and how it works. In this video, we're going to dive deep into this theory and explore the intricate biological machinery behind what might be the fundamental building block of intelligence, the cortical column. For over a century, since the pioneering work of Ramon y Cajal, autonomists have known that the entire cortical sheet shares a common blueprint. No matter where you look, the basic circuitry and cell types, arranged into 6 characteristic layers, appear to be the same. The next turning point came from the work of neurophysiologist Bernard Mountcastle, who revealed how this anatomy translates into a stunningly consistent function. Using microelectrodes to listen to neural activity, he discovered a key principle. As he lowered the electrode straight down through the cortical layers, he found that all the cells in the vertical column, about half a millimeter wide, were all doing the same job. In the somatosensory cortex, he discovered, all the cells in a column responded to a stimulation on the exact same patch of skin. Soon after, David Hubel and Torsten Wiesel famously confirmed this columnar principle in a completely different system, the visual cortex. There, they found columns of cells that were all tuned to respond to a line of the exact same orientation. So the evidence was overwhelming. The neocortex is not a collection of many unique structures. It is built from a single type of processing module, the 6-layered column, replicated over and over again. This led to the Columnar Hypothesis. If the functional hardware is universal, then the fundamental computation, the algorithm it performs, must be universal as well. Seeing, hearing, language, and abstract thought might all be different manifestations of the same underlying neural process. The only thing that changes is the data being fed into the columns as input. This reframes our entire quest. To understand the neocortex, perhaps we don't need to find hundreds of different solutions for all sorts of different problems. We just need to find one universal algorithm that powers each of these information processing units. And this kind of canonical computation is exactly what the thousand brains theory aims to describe. Many modern theories of brain function converge on a single powerful idea, that the fundamental purpose of neural computation is to build a predictive model of the world. This internal model allows us to understand the present, plan the future, and navigate uncertainty, all to increase our chances of survival. If you're interested in this, I covered related frameworks like predictive coding and the free energy principle in previous videos. The thousand brains theory takes this concept and adds an important twist. It proposes that the brain doesn't build one single monolithic model of the world. Instead, every single cortical column is its own complete modeling system. Think of it this way. Rather than being one giant centralized factory, the cortex is like 150,000 parallel mini-factories. Each one learns its own complete model of things, from simple lines to complex objects. Your singular rich perception of the world is the result of these thousands of mini-brains constantly comparing notes and voting to reach a consensus. This elegant idea immediately solves a major evolutionary puzzle. How did the human brain become so powerful so quickly? Evolution did not have to invent hundreds of new brain components specialized to different cognitive functions and later figure out how to wire them all together properly. Instead, it had to do something much simpler. Add more columns. Adding more instances of the same universal module vastly increased the brain's computational power. You're not adding fundamentally new kinds of machinery, you're simply expanding the pool of voters, which leads to a more detailed and robust model of the world. So how does one mini-factory, a single cortical column, actually work? The core idea revolves around learning the structure of things through sensorimotor coupling. To understand it, let's begin with a simple analogy. Imagine you're in a pitch-black room with a statue that you can't see, and your goal is to understand what that object is simply by touching it. If you only focus on the sensation from your fingertip, you will get a sequence of disconnected feelings like smooth cold marble, then sharp metallic edge, followed by rough carved stone. You will have a list of features, but no real understanding of the statue itself. The key is to also track your own movement. Let's say you start at the statue's foot, but you don't know it. Your brain registers the sensation rough stone and anchors it to some starting position on your mental map. Let's call it 0, 0. Then you move your hand up 1 meter. Your brain receives a copy of this motor command and updates your position on the map to something like 0, 10. At this new location, you feel smooth marble. You've just done something really important, binding a sensation to a location derived from movement. You continue this process, move, update location, sense, and add the new feature to your map. After exploring for a while, you no longer have a simple list of features. You now have a rich structural model, where features are anchored to specific locations. This map is what the theory calls a reference frame. Once a column has this map, it gains the superpower of prediction. By knowing its current location on the statue, it can predict what it would feel if it moves to a new spot. This process of tracking your location based on a sequence of movements is a known neural computation called path integration. It's how you can navigate in the dark and find your way back to where you started. This brings us to a profound application of the theory. For this process to work, every single column must have its own sensorimotor system. While it's obvious for columns in the motor cortex, the theory makes a bold prediction. Every other column also has a motor output. But what motor means can change. In the visual cortex, for example, columns send commands to muscles that move your eyes. And in the brain's more abstract areas, a motor command might be simply an instruction to shift your attention or recall a specific memory. So, the universal algorithm is this constant sensorimotor loop, which carries out the binding of sensory inputs and locations. Great! Now let's see how this process is physically implemented in the 6 cell layers of a real cortical column. To understand the origins of the cortical column, it's helpful to step back in evolutionary time. Long before the advent of the 6-layered neocortex, our ancestors faced the fundamental challenge of navigating the world, memorizing locations of food and shelter, and planning efficient routes. This complex job is handled by the specialized set of structures deep in the brain called the hippocampal formation. At a high level, it has 3 main components that work in tandem: the medial and lateral parts of the entorhinal cortex and the hippocampus itself. Now, because these structures are evolutionarily older, their architecture is different. The hippocampus is an example of what's called allocortex, which is composed of only 3 layers. And the entorhinal cortex is an evolutionary bridge between the ancient allocortex and the modern neocortex. It also has 6 layers, but its internal wiring is different. It doesn't have the same columnar structure. In broad strokes, hippocampal formation works as follows. The medial portion of the entorhinal cortex encodes pure location information. It contains famous grid cells, neurons which act as a universal coordinate system, firing in a hexagonal grid as the animal moves, constantly tracking its location. But a map is useless without landmarks. The sensory what signal, sights, sounds, and smells, is encoded in the lateral entorhinal cortex. These 2 information streams, what and where from both divisions, are then sent as the input to the hippocampus. This is where the crucial binding takes place. Pyramidal neurons in the hippocampus, called place cells, fire encoding a location in a specific context. This is why, while a grid cell's firing pattern is mostly fixed, Response properties of place cells completely change if you alter the sensory features of the environment, a phenomenon called remapping. If you're interested in more detail on hippocampal formation, we covered place and grid cells in earlier videos. Now, here is the stunning twist of today's story. The thousand brains theory proposes that this exact principle, binding a what signal and a where signal to form a specific model, is the universal algorithm of the cortex. The brain essentially took the entire modeling toolkit from the hippocampal formation, miniaturized it, and copied it into every single cortical column. So let's follow that blueprint. Let's examine the six-layered architecture of the neocortex and try to locate where the analogs of this ancient circuitry ended up. The most straightforward component to locate is layer 4. This is the column's primary input port, receiving sensory data from the thalamus. When you see a specific edge or feel a particular texture, it's neurons in layer 4 that fire first. This is the what signal, making layer 4 the direct analog of the lateral entorhinal cortex. Next, we need to find the analog of the medial part, the division which generates the where signal. This crucial job of location tracking is thought to belong to layer 6. One of the key predictions of the thousand brains theory is that every column contains its own set of grid cell-like neurons in layer 6. These neurons form a coordinate system, tracking the location of the column's associated sensor, whether it's the position of the finger, the direction of our gaze, or even an abstract cognitive variable. And indeed, there is a growing body of evidence showing these grid cell-like properties throughout the cortex. But for these grid cells to work, they need to know how the sensor is moving. This brings us to layer 5, the column's primary action output. When a layer 5 neuron fires to generate a motor command, like move the eye, along with sending that command to effector muscles, it also sends an efference copy, an internal carbon copy of that command, to its neighbors in layer 6 within the same column. The cells in layer 6 then use this movement information to perform path integration and update the column's current location on the map. So we found our inputs, what from layer 4 and where from layer 6, calculated by motor commands of layer 5. Now we need to bind the two together. This is the job of the upper, layers 2-3 of the cortical column, which makes it a loose analog of the hippocampus. These layers receive both the sensory input from below and the location context from deeper layers. Technically, the location information is not sent directly up the column. Instead, neurons in layer 6 communicate with upper layers via thalamus, broadcasting positional information. A layer 2-3 neuron then learns to represent complete objects by binding sensory features with location. This is where the stable predictive model is formed. Finally, there is layer 1, the very top layer. It contains very few neurons and is mostly composed of neural wiring, dendrites and axons of neurons whose cell bodies are located in other layers. This is where the location signal from layer 6 arrives, priming the dendrites of the neurons below and setting up the column's predictions. And with that, we have the complete circuit, a beautiful self-contained modeling machine. Each column uses a sensorimotor loop to build predictive models by binding sensory features to locations on the map. And what the column actually does, whether it's filling a coffee cup or solving a math problem, simply depends on the type of information arriving at layer 4 and the kind of sensor, physical or abstract, that the column controls. But if each column acts as its own mini-brain, how do we perceive the world as a single unified whole? This brings us to the crucial idea of voting. Imagine you're grasping a coffee cup in the dark. Your fingers all project two different sets of columns in your brain. Your thumb touches the handle, so its columns sense a C-shaped ceramic object. Your index finger is on the rim, so its columns sense a circular edge. In each column, the neurons in layer 2-3 represent possible explanations for the sensation. But a single sensation is ambiguous. The circular edge, felt by your index finger, could belong to a coffee cup, or a saucer, or a wine glass. As a result, multiple sets of neurons, each representing a different object, become partially active. The column is holding several hypotheses at once. The columns of the thumb face the same problem. Their C-shaped sensation is consistent with a coffee cup handle, a teapot spout, or even a cabinet drawer, causing several groups of neurons in layer 2-3 to become partially active. Notice the crucial point of overlap. The coffee cup is the only hypothesis that appears on both lists. It is the only object consistent with both the C-shaped handle and a circular rim in their correct locations. The thousand brains theory proposes that columns agree on this shared hypothesis through a rapid process of voting. This reveals a key architectural feature. Each column has two distinct outputs. The first, from layer 5, sends motor commands to act on the world, as we saw previously. The second, from layer 2-3, sends signals sideways to other columns. Its purpose is not to move a muscle, but to reach a consensus by refining predictions and resolving ambiguity. Here is roughly how the voting process unfolds. In the first milliseconds after you place your fingers on the cup, the network is a noisy chatter of conflicting hypotheses. But very quickly, the neurons in layer 2-3 in different columns begin to vote. Consider the coffee cup neurons in your index finger column. They receive convergent evidence, the bottom-up sensory data for a circular rim, and supporting votes from the coffee cup neurons in your thumb column. This reinforces the coffee cup hypothesis by driving those neurons to fire more strongly. Meanwhile, the wine glass neurons are in trouble. They have local sensory evidence, but they receive no supporting votes from the thumb column. Lacking this reinforcement, their activation fades, and they're suppressed by the strong activation of their coffee cup neighbors. This creates a kind of rich-get-richer cascade. As the coffee cup neurons fire more strongly, they send out more powerful votes, which further reinforces the coffee cup neurons in other columns. The result is a rapid convergence. In a fraction of a second, the one hypothesis that is mutually consistent across the network amplifies itself into a stable, unified consensus. All competing inconsistent hypotheses are silenced, and your brain arrives at a single unified perception. So far, we've used concrete examples, like touching a statue or holding a coffee cup. But the real power of the thousand brains theory lies in how it scales from physical motion to higher, more abstract forms of human thought. The theory makes a beautiful and simple proposal that the underlying algorithm is identical. It's just using a different kind of sensor and a different kind of movement. The input arriving at a column's layer 4 doesn't have to come from our skin or eyes. It can come from the layer 2-3 output of other columns. In this view, the stable perception of a coffee cup from a lower-level column can become the sensory input to a column higher in the cortical hierarchy. And what is the motor command? Well, instead of moving a finger, this higher-level column issues a command to shift the attention, directing which sets of lower-level columns provide the next piece of input. Imagine tackling a complex logical problem. You are, in essence, navigating a conceptual space. Each step, like recalling a fact, applying a rule, or focusing on a sub-problem, is a mental move that takes you to a new location in the problem's abstract terrain. As you trace this journey, guided by rules learned from past experience, your cortical columns are executing the very same algorithm they use when exploring a statue in the dark. This offers a compelling and unified view of the neocortex, a vast network of thousands of mini-brains, each learning a predictive model of its surroundings by binding sensations to locations on a reference frame derived from movement. Of course, this theory is still a work in progress, and many aspects of brain function don't fit so neatly into this picture. But it is an important first step, and it provides a powerful conceptual framework of thinking about intelligence in a new way, one that brings together anatomy, physiology, and behavior under a single unifying umbrella. A central theme of our discussion today is that learning is not a passive process. The brain builds its powerful models not just by seeing, but by doing, by moving, interacting, and actively exploring the problem. This philosophy of active learning is exactly why I'm excited to tell you about our sponsor, Brilliant.org. Brilliant is an innovative platform designed to be a uniquely effective way to learn. They help you become a better thinker and problem solver through bite-sized, engaging lessons in STEM fields. What makes Brilliant so powerful is their focus on hands-on experience. Rather than just passively reading or watching a lecture, you get to learn by doing, exploring interactive diagrams and practicing real-world problem solving. I'm a big fan of this approach because Brilliant builds complex ideas up from first principles and helps you develop an intuitive understanding of complex topics. They have an incredible library of courses, crafted by an award-winning team from places like MIT, Caltech, and Google. So whether you want to strengthen your math fundamentals or dive into advanced topics like neural networks, Brilliant is a phenomenal way to embrace your curiosity. To get started, head to brilliant.org/ArtemKirsonov to claim your 30-day free trial of everything they have to offer, plus a 20% discount on annual subscription. If you enjoyed the video, share it with your friends, subscribe to the channel if you haven't already, and press like button. Stay tuned for more neuroscience and machine learning topics coming up.